So let's wait for 2 to 3 minutes, then we'll start the section. Let's wait for others so that they can join. Before that, let me ask you whether you have any doubt uh, in the previous section, or you have any doubt in the assignment. Any doubts so that I can clarify your doubts in between. If you have any doubt, then you can write it in the chat box, or you can unmute yourself and ask the question. I have already unmuted you, so you can ask the question anytime. Book to practice the problem, some problem in the assignment. Okay, so the book, mm, I would suggest whatever sir suggested in the uh, weekly course. Otherwise, I will upload some books in the Google Drive also if you want to go through any reference book. So I think you have the link to my Google Drive folder where I upload all the content or the all the slides of the week. So I think you have the access to the link. So let me upload the books there so that you can refer to that book and if you have any doubts. So assignment problem, I think whatever the problems they have asked or they have put in the assignment, I think if you go through the slides and whatever taught in the course, you can easily solve the assignment problem. And if you have doubt, then you can ask me anytime in this live section. So I will try to solve your doubts. If not, I will also, if not now, not in this section, then I will try to solve it in the next session. So feel free to ask me the doubts, whatever you have in the assignment or in the concept, whatever doubts you have. So you can, that is why we have live section in each week so that you can clarify your doubts. So I would suggest for the assignment as well as for the exam, please go through the lecture slides very carefully because whatever will be asked, it will be from the concept, whatever taught in the lecture slide. Nothing will be asked outside. So if you go through the lecture slide and the videos again and again, I think you can solve the problems, as well as in the live section also. I not only solve the problems, I also revise the concept which is taught in this week. So this will help you to recall the concept, as well as so that you don't have to go through the video again and again. So please try to attend the live section. I'm noticing not enough people are attending the live section, so please try to attend it, because it is where you can ask your doubt freely. And it is like a direct interaction. It's like whatever you have doubts, you can clarify your doubts immediately. Otherwise, a discussion forum is there also where you can ask the doubt, but the response will be late. But if you have any doubts, you can clarify in this live section. So for the book, let me upload the books in the Google Drive so that you can go through the books. Any doubts, other people who have joined? Otherwise, we'll start the section. Okay. So let us start the section. So hello all, I'm Gitanjali Jaina. I'm a PhD scholar from IIT Delhi. So I welcome you to I think this is the fourth live section of this course, Introduction to Laser, which is taught by Professor M.R. Senoy. So I will be TA for this course, where we will go through the concept as well as go through the equation that is taught in this week. And we will also solve a few problems that is related to the concept, as well as I will clarify the doubts that you are having in any of this concept, as well as the assignment problem. So let us recall whatever taught in the previous lab section. So in the previous lab section, we went through the two-level atomic system, as well as three-level atomic system. So in two-level atomic system, we saw that the population, the lasing, lasing will not be possible in the two-level system. Whatever the pump is at the steady state, the lasing action cannot be possible in the two-level system. But in the three-level system, it is possible to achieve the population inversion and amplification of the lasing, amplification of the input radiation, if the pumping rate, if it is greater than the spontaneous lifetime. So these are taught, and one of the example of this three-level system is the Ruby laser. Uh, and we went through the rate equation of this three-level system, and we solve what is the what are the approximation that is used to what are the practical approximation that we have used uh, to finally find out what is the condition for population inversion in the three-level system. The first approximation that we have made is these are all practical approximation. It's not like it's not valid in the real life problem. So the first approximation we made is T32 is much greater than T31. And the second approximation that we have made is this is T32 is much greater than T21, which will ensure that the population inversion will be possible in the laser medium. And finally, we found out that the condition that is required for the population inversion as well as the amplification is WP, that is the pumping rate, must be greater than T21. So, and for the threshold amplification, we have delta n, which is n2 minus n1 is 0. And from that, we find out what is the threshold condition for the pumping rate, which is WP is T21. So T21 is, you already know, it is related to the spontaneous emission lifetime from 2 to 1, which is easily measurable experimentally. So if you know the spontaneous emission lifetime, then you can easily find out what is T21. And from that, you can find out what is the threshold pumping rate that is required to initiate the amplification. That is, this is the minimum value that should be the pump should have for amplification to start in the medium. And from that, we saw what is the gain saturation. And previously, we have assumed, if you recall, we have assumed delta n is delta n0 divided by 1 plus I nu by Is. So please remember all these equation so that you can easily solve the problems. So this we have assumed previously, but in the 3 level or 2 level, or we'll see in the 4 level, we have already derived this equation. Delta n is delta n0 divided by 1 plus I nu by Is. So these are all the derivation of this equation. So if you see, we found out how the delta n is delta n0 1 plus I nu by Is. And delta in n0, it is independent of the input intensity of the input radiation. And from that, we see what is the gain saturation condition and how the gain, how it is varying with the intensity of the incoming radiation. And from that, sorry, we saw two conditions. First is where the input radiation is much less than the saturation intensity, and in that case we see that the intensity will increase exponentially whenever the intensity of the input radiation is much less than the saturation intensity of the medium. And when the intensity of the input radiation is greater than, that is the opposite extreme, where I nu is greater than Is, then we'll see that the gain, if you recall, if you see this graph here, the intensity for I nu less than Is, it is almost constant. So that's why we have a, if in this case, we can take gamma nu as gamma 0 nu, which is small signal gain coefficient. So it is a constant value. That is why we see, according to the equation, I equal to I naught e to power gamma L. So in this case, gamma L is nothing but gamma 0 L. So as gamma 0 is constant, so if we increase the length, then the intensity will increase exponentially. But when, if you see this region, here the intensity, the gain is it is decreasing with respect to the intensity. So that is why if you see this region, in this region I nu is much less, much greater than I is. So that is why we can take gamma nu is a constant, it is almost zero. So gamma 0 we can take as 0. So from this you can easily see I is 0. So for this we'll see a constant curve after some time. Okay, so these are the two conditions that we'll see in the gain curve whenever the intensity is greater than Is or less than Is. So this is how it is varying. Then we solve the problems that is related to this concept, 2 level and 3 level energy system. So please go through the problems. So it will help you, because in the final exam will, I think the problems will be mostly MCQ, and I have talked with the team also. The problem will be like MCQ as well as some numerical problems will be there. So please go through the problems that I have solved as well as the assignment problem. Okay, that is enough to pass the exam. So, and please attend the live section. So, if you not, then you won't be able to clarify your doubts, as well as it is also beneficial for you because I am revising the concept also. So, okay, so let us see what is 4 level system. So, these are all about 3 level system that we have seen now also. So let us directly jump into the 4-level system. Okay, so these are all about 3-level system. So okay, so let us again please go through the 3-level system. So in the 3-level system, we have the gain is gamma 0 nu divided by 1 plus I nu by Is. So from that, we see what is the intensity expression for saturation intensity and what is tau is, and what is how the pumping rate it is related to the spontaneous emission lifetime, and what is the approximation we have used to find out what is the condition for amplification. And from that, if you see, when pumping rate increases, the value of Is also increases, and when pumping rate increases, the gain curve also increases. If you see this curve, this is the curve for different pumping rate. So if you see WP3 is greater than WP2 is greater than WP1. So W is the pumping rate that is used to pump the system. So under this 3 pumping rate, we see that as we increase the pumping rate, the gain curve also increases. So if you see the red curves here, you see the edge, the pumping rate increases, the such small signal gain coefficient also increases. And if you see the saturation intensity, that is the intensity where, so saturation intensity, what is saturation intensity? So this is the intensity when the gain is half of the small signal gain coefficient. So if you see the expression gamma nu is gamma 0 nu divided by 1 plus I nu by Is. So when I nu equal to Is, this gamma nu will be equal to half of the small signal gain coefficient. So this is the definition for saturation intensity. Now, when we increase the pumping rate of the system, what will happen to this saturation intensity? So when we increase the pumping rate, the saturation intensity will also increases. So for this, we'll see here WP3 is greater than WP2, which is greater than WP1. In this case, we will have IS 3 greater than IS2 greater than IS1. Okay. And similarly, the small signal gain coefficient also increases. And one of the example of this 3-level system is the Ruby laser, where it is nothing but a chromium doped aluminum oxide matrix. And this is the schematic, I think all of you are familiar with the schematic of 3-level, 2-level, and 4-level system. So if you see this, if you take the Ruby laser, then we have the N, that is total number of atom per unit volume is approximately 10 to the 19 per cc. Cc is cubic centimeter. And the pump we use, it is around green laser. Lambda P is around 500 nanometer. And if you want to find out what is the threshold pumping rate, then it is equal to T21. So now, if we have, you know that T21 is inversely proportional to the lifetime of the excited state, which is tau L, 1 by tau L. And for the Ruby, the tau L is in the order of 3 millisecond. So if you put the 3 millisecond in this equation, we will get the T21 is 1 by 3 into 10 to the minus 3 second inverse. So you got you have tau L, so you can easily find out T21. From that, you can easily find out what is the threshold pumping rate required for the amplification in the system. From this, let us see what is the pump power required for the threshold condition and what is the pumping rate. So at the threshold, so please recall what is the threshold condition. So at the threshold, we have delta n equal to 0. So delta n is 0 means n2 minus n1 equal to 0, and that implies n2 equal to n1. Now you already know that the total number of atom, that is n, it is equal to n1 plus n2. And at threshold n1 is equal to n2, that means this will be from this you can easily find out what is n1. So n1 must be equal to n divided by 2, right? So at threshold we have equal number of atom in the ground state as well as in the excited state. So if you see, this is what is written here. Uh, in the three level system, what happens? The atoms get excited to this higher energy level, and from this energy level, what happens? It will rapidly decay to the intermediate state, which is the metastable state. So that is why it is a fast transition. So that is why we are assuming that N3 equal to 0. So whatever atoms that are excited from the ground state, that is from here to here, it will rapidly decay to this second energy state, which is 2. So that is why we are assuming that N3 equal to 0 here. So total number of atom will be equal to N1 plus N2. So N3 is 0. So total number of atom is N equal to N1 plus N2. And if you want to find out what is N1 and N2, which is nothing but equal to total number of atom divided by 2. Now, if you want to find out what is the pumping rate at threshold, so this will be equal to WPT into N2. So and WPT is nothing but T21, right? So T21, uh, this will be equal to T21, and N2 is nothing but N divided by 2. And if you want to find out power from this pumping rate, so you have to multiply what is the energy of this pump. So H nu P is the energy of this pump. So whatever pump you are using, what is the frequency? So if you multiply the pumping rate with the energy of this pump power, then you can easily find out what is the pumping power required for at the threshold condition. Now you have to put what is WPT, what is N divided by 2, H and UP, which is already given here. So T2N is already given, and WPT is nothing but T21, and lambda P is 500 nanometer. So from that you can easily find out what is nu P. Nu P is nothing but C by lambda. So if you put all these values, what you will get? The pumping power at threshold is nothing equal to 660 watt. So which is in the order of 1 kilowatt. So this is how you can calculate what is the pumping power required at the threshold condition. Okay. And now let us see what is the 4-level system. So similar to 3-level system, where the transition is mostly focused around the 3 energy level. Here we have 4 energy level. Okay, so it's not like the system has only 4 energy level. It's like when we say it is a 4-level system, we are basically focusing on the energy level that is participating in the lasing condition. And if you see in the 4-level system, mostly 4 energy level they participate in the lasing condition. So these are the schematic of a 4-level system. So N1, this is the ground state. N2 is the population in the second state. N3 is the population in the third state, and N4 is the population in the higher energy state, which is fourth state. So now if you see in this 4-level system, the lasing, the amplification is occurring between this 3 and 2 level. So between this 3 and 2 level, the amplification is happening. So now let us see what is the condition for amplification in this 4-level system. So we have a pump here which have energy H nu P, and this will excite the atoms from this ground state to the fourth state, and from this it may follow the stimulated path or spontaneous emission path, which is T41. and it may happen the atoms will make a transition to this third energy level from the fourth, or it can make a transition from this fourth level to the second energy level, and from the second energy level it make a transition to the first energy level. Now for the you are saying that here the amplification is happening between this energy level, right? And what should be the condition for increasing the, so let me okay, so the thematic is also here. So if you want, so lasing is happening between these two states. So if you want to increase the, so that means this N3 and N2. So N3 should be greater than N2. So to increase the population in this state, what should be the condition? So T43, that is the rapid decay to this third energy level, it should be greater than T41 and T42. Okay, so this should be greater than T41 and T42. That is this, it should be greater than T41 and T42, so that the atom will rapidly decay to this third energy level, and they get populated here. So one condition we see T43 is must be greater than T42 and T41. Now to maintain the population inversion, that is N3 should be greater than N2. So that means the atoms that is in this state, it should, whatever atom is making transition from third energy level to the second energy level, it should rapidly decay to the first energy state, so that the number density N2 is less than N3, right? So this means that this T21, it should be greater than T31. Okay. So should be greater than T31, should be greater than T32, not 1. Okay. So please correct this equation. So it's already written here also. There is a mistake here. So T21 must be greater than T32. Are these two condition? Is it so? These two condition that we have derived. Is it clear to you? So these are the two condition in the four level system. Okay. So please remember these two condition. This is required for the amplification process between the third and second energy level. Now let us see what is the rate equation. So rate equation. So for this rate equation, we will neglect the terms that is not required. That is T21, T41. We will neglect this two terms. Okay. So if you see the fourth, this state, this pumping from first to the fourth state, it will increase the population, and the de-excitation from fourth to one state, it will decrease the population in the fourth energy state, right? So that means dN4 by dt is Wp(N1) minus N4. And the second term is nothing but the rapid first decay to the third energy state, which is T43 and 4. So this decay will decrease the population. There are two excitation, this one and this. That is Wp and 4 and T43 and 4, which will decrease the population in the fourth state, and WpN1, it will increase the population of N4. Now this is for fourth state. Now we'll see what is the rate equation for the third state. So for the third state, what we have, this WL N2, it will increase the population, and these two excitation, de-excitation, that is WLN3 and T32N3, it will decrease the population in N3, And what another transition is from N4 state, which is T43 N4. It will increase the population. So these are the two equations for the fourth and the third state. We'll see the second state now. So for the second state, what are the transition we have? We have one transition from this to this, that is the second state to first state, which is T21 N1. So this will decrease the population. So T21 N2, sorry, T21 N2, it will decrease the population. And one that is decreasing the population is WL, that is this pumping, WL N2. So WL N2 will decrease the population. And these two transition, the black and the red line, it will increase the population. So the black is WLN3 and the red is T3 to N3. So this will increase the population of the second energy level. Now let us see what is the rate equation for the first energy level. So first energy level, there are total three transition, right? This pumping, this is T excitation, and this is from 2 to 1. So this means WP and 4, that is this WP and 4, it will increase the population. WLN1, which takes the atom from first to the fourth state, it will decrease the population. And the T21N2, which makes the atom from second energy level to the first, it will increase the population of first energy level. So these are the final equation. So please go through this equation of 4, 3 and 2 level system, because this is where you can find out what is the steady state condition, and from that you can find out what is the threshold condition also. So please go through the equation. Equations are also required to solve any assignment problem or any problems in the exam. So now if you see what is the total number of atom in the system, which is nothing but N1 plus N2 plus N3 plus N4. So if you take out N1 from here, it will be N1, 1 plus N2 by N1 plus N3 by N1 plus N4 by N1. And at the steady state, what is the condition we have? At the steady state, the population, and that is the atomic population, whatever present in the energy level, they remain constant. So that is why we say it is a steady state. So that means the change of this population density will be zero at steady state. So this means dn3 by dt equal to 0, dn1 by dt equal to 0, similarly dn2 by dt equal to 0, and dn4 by dt equal to 0 at the steady state. Now if you put this condition one by one, you can easily find out what is this ratio N4 by N1, N3 by N1 and N2 by N1. So N4 by N1 you can easily find out using this condition, equation 1. So if you put dN4 by dt equal to 0, you found that N4 by N1, it is nothing but WP by T43. Okay. And using now if you take equation 4, you can easily find out what is the ratio for N2 by N1. And using these two equation, I think this algebraic equation you can easily find out. So I'm not going through this equation in detail. So if you have doubt in any of these steps, you can ask me. Otherwise, let us quickly go through the final terms. So N3 by N1. So N3 by N1, it is nothing but this equation WP T21 plus WL divided by T21 T32 plus WL. Similarly, if you for population inversion, what we need? We need how delta N is related to this pumping rate. So if you find out what is delta N using this C and B equation, you find out this delta N by N1 is this equation. And delta N, it is the population. It is the difference between the atomic population between the levels at which the lasing condition is happening. So you saw that this for 4 level system, there are 4 energy levels, and the lasing condition is happening between this 3 and 2 level, right? This is 3 and 2. So that means the delta n is now n3 minus n2, not n2 minus n1. So please be careful whenever you are taking delta n. So always take the delta n between the delta n is the the population density difference between the energy level at which the lasing condition is happening. So delta n, if you find out, this is equal to this equation. And from this equation, if you see for delta n, so population inversion means delta n should be greater than 0. So that means this negative, this difference term, it should satisfy this condition, which is T21. It must be greater than T32. Okay. So for the 4 level energy system, we have T21 should be greater than T32. If you recall in the 3 level system, this T21 it is less than T32. So don't get confused between the different types of energy level. Please read the question properly, whether it is asking about 3 level or whether it is asking about 4 level. According to the type of the level we are considering for lasing condition, the condition will vary. So for the 4 level, we have T21 is greater than T32. And similar to the the way we have derived delta n equal to delta n 0, 1 plus I nu by I is. Here we also we can derive this equation. It is delta n is delta n 0 divided by 1 plus I nu by I is. And from that, we can easily find out what is how the gain coefficient, saturated gain coefficient, it is related to the intensity of the incoming radiation. So again, we'll see the same type of relation, that is delta n is delta n 0, 1 plus I nu by I is, and gamma nu is gamma 0 nu, 1 plus I nu by I is. And the curves will be also similar. That is, if you have uh, if you want to plot gamma nu is gamma 0 nu 1 plus I nu by I is, then the plot will be like this. So for small intensity, it will be a constant. If you see this region, so let me use different color. So if you see this region, so here the gain coefficient is almost constant. So for I nu much less than is, so what I mean, I nu much less than is, the gain is almost constant, and as the intensity increases, the gamma now will gradually decreases. Okay, and if you use two different type of pump, that is WP2 and WP1, where WP2 is greater than WP1, then we'll see a gain curve like this. So similarly, we have seen in the 3 levels when WP2 is greater than WP1. So that means the saturation intensity of second is greater than saturation intensity of 1. Similarly, the gain coefficient, the small signal gain coefficient, that is gamma 0 nu 2 is greater than gamma 0 nu 1. So please go through this relation. These are easy relation. You can, if you know what is the relation between gamma and I, then you can easily plot what is the variation of gamma with respect to intensity and what will happen when we use different type of pump. Okay. So before solving some problems, let us summarize what is the condition in the four level laser amplifier. So in the four level, we have four energy level that is participating in the amplification process, and the amplification in the four level, it is happening between the second energy level and the third energy level. So that means the delta n will be n3 minus n2 here, and this is the relation we get while deriving the delta n. And the approximation that we have used, it is T43, and these are all practical approximation. So T43, it should be greater than T42 and T41. So why should be T43 greater than T42 and T41? So for delta n to greater than 0, we want N3. We want atoms to populate in the third energy level. So that means this transition should be first, should be a fast transition. So that is why we have T43, it should be greater than T42 and T41. And for population inversion, we saw T21 should be greater than T32. So that is, what is the meaning of this? So this means whatever atoms that are present here, it is rapidly decaying to the first energy level. So that this N3 minus N2 remains positive during the transition. Okay, and one of the example of this four level system is Nd:YAG laser, where we dope neodymium atom in the yttrium aluminum garnet. Okay, so this is all about the four level system. So before solving the problems, do you have any doubts in the four level system? Any of the step? Otherwise, we'll solve the problem and we'll move to the next part. Please go through. Sorry. Please go through all the rate equation as well as all the approximation that we have made for the three level, two level system. Okay. So these are crucial to find out what is the amplification condition and what is the condition required for the population units. So I think let us proceed to the next part then. So we'll solve few problems now. Then we'll move to the concept of we'll study what is neodymium Nd:YAG laser in details and how amplification occurs in the Nd:YAG laser. So the first question is, it's a easy question, I think. So let me read out the question for you. So the question says, for a two-level system, the population of atoms in the upper and the lower level. These are 3 into 10 to the 18 and 0.7 into 10 to the 18 respectively. The population of two levels are there and populations are given. Okay. Now, if the coefficient of stimulated emission is 3 into 10 to the 5 meter cube per watt per second cube, and energy density is 9 joule per meter cube hertz. What is the rate of stimulated emission? So these are the information that is given to you. That is the population of, so we have two energy level, N2, N1, and we are given what is the value of N2, what is the given value of N1, and the coefficient of stimulated emission. and the energy density. And what is the rate of stimulated emission? So if you recall the rate of stimulated emission, it is nothing but dN2 by dt is equal to, it is related to the energy density as well as it is related to the B21, that is the coefficient of stimulated emission from 2 to 1, and it is related to the N2, that is the population of the second energy level. Okay, and these are all given to you. N2 is already given. This is 3 into 10 to the power 18. B21 is given 3 into 10 to the power 5, and energy density is 9 joule per meter cube hertz. So if we put it, you can easily find out what is the rate of stimulated emission, which is, it is 8.1 into 10 to the power 24. Okay, so this problem was easy. If you can recall what is the rate of stimulated emission, then you can easily find out what is the answer to this question. In the second problem, it is also a conceptual problem. So this we have already seen now. So let me quickly read this question for you. So the question says, the electronic energy level of a molecule is shown in the following figure. That is, this is the four level energy. First state. This is level day second, third, and fourth. And the gamma is a denote the decay rate for a transition from the level I to J. So these are decay rate. Gamma to 1, the decay rate from 2 to 1. Gamma 2, 3 is the decay rate from 2 to 3. Gamma 3, 4 is the decay rate from 3 to 4. And gamma 4, 1 is the decay rate from 4 to 1. And what is given? The molecules are optically pumped from the level 1 to level 4. So, level 1 to level 2. So it is initially we are pumping the atoms from this state to from first to level 2. For a transition from level 3 to 4 to be Lasinger transition, the decay rate have to satisfy. So it is saying there is a Lasinger condition that is happening between 3 and 4 state. So for this to happen, what is the Lasinger condition? So we have all, if you recall, we have already seen what is the condition. That is this rate gamma 41. It should be greater than all the decay rate, and the gamma 34, it should be less. So let me clearly write what is the condition. So if you see, we have already seen this gamma 23, it should be greater than gamma 21, right? Should be greater than gamma 21, so that the uh, the atomic population in the third state will increase because of the rapid decay of atoms from 2 to 3 state. And gamma 41, it should be the highest decay rate, so that these whatever atoms that is making a transition from 3 to 4, it is rapidly decaying to first. So this is what written here. So if you see, I think C option is correct. So this means I have clearly I have clearly wrote why this condition should be there. So it is saying the state 3. So if you see, this is 3, this is 4, and 3 is a metastable state. So this means the gamma 34, it should be lowest to enhance the population inversion, and gamma 23, it should be greater than gamma 21 to increase the number density of atoms in the metastable state. So if you see these two conditions, then it is easily satisfying in this option. So gamma 41 should be greater than gamma 23, should be greater than gamma 21 and gamma 34. So this is the second uh, problem. So for the third, it is also easy. Third problem, it says a laser beam of intensity I0 is incident normally on a medium of thickness 2 millimeter, and the intensity of the transmitted beam is 0.025 I0. Then it is asking about what is the absorption coefficient of the medium in meter inverse up to 1 decimal place. So if you recall, what is the intensity relation? I equal to I naught e to power gamma L, right? So with respect to gain coefficient, we have I equal to I naught e to power gamma L. So if you want to write it in terms of absorption coefficient, what we have? We have I0 e to power minus alpha L, because gamma is negative of alpha. The gain coefficient is negative of absorption coefficient. So that means the equation for this is I equal to I naught e to power minus alpha L. And I, it is already given. It is nothing but 0.025 I naught. And L is also given, which is 2 mm. So if you put it in the equation, you can easily find out what is the value of alpha. So alpha is nothing but minus of ln 0.025 divided by 0.002. So if you find out the answer, it will be up to 1 decimal place, it is 1844.4. Okay. So are these three problems clear to you? All these problems? Otherwise, we will move to the next. Okay. So let us move to the next problem then. Vishal, you have any doubts? Okay. So let us move to the next problem then. So the next problem is the energies of the three lowest state of an atom are E0 equal to minus 14 electron volt, E1 equal to minus 9 electron volt, E2 equal to minus 7 electron volt. And the Einstein coefficient are A10 equal to 3 into 10 to the power 3 second inverse, A20 is 1.2 into 10 to the power 8 second inverse, and A21 it is 8 into 10 to the power 7 second inverse. And if a large number of atoms are in the energy level E2, then what is the mean radiative lifetime of this excited state? So let me draw the schematic of this problem. So there are three states, which is E0, E1, and E2. And these energy levels are given. So this is minus 14 electron volt, minus 9 electron volt, and minus 7 electron. So these are given. And the Einstein coefficient of 1 A10, that is this one. This is given A10, A20 is also given. And what is given? A21. So this is also given A21. Now it is saying if a large number of atoms are in the energy level E2. So there are large number of atoms in this excited state E2. Okay. So if there are large number of atoms in the excited state E2, they will decay to the lowest energy state. Then it is asking what is the mean radiative lifetime of this excited state. So it is asking about the mean radiative lifetime when you have a situation like this. Okay. So now let's see how we can solve this problem. So if you see this energy level, so there are two transition, right? From the so please see what are the transition, what are the possible transition from this state. So possible transition from this state is A21 and A20, right? So the radiative lifetime, it is related to this transition only. Don't take A10 because it is from 1 to 0. So it is not required for this problem. So that means we have two Einstein coefficient A20 and A21. So if you recall, what is the radiative mean radiative lifetime, this is related to this equation. If there are more than two transition, then we can say 1 by the total, 1 by tau 2 is the mean radiative lifetime. So 1 by tau 2 is equal to 1 by tau 20, which is the transition from 2 to 0, and tau 21 is the transition from 2 to 1. So it is related to 1 by tau 20 and 1 by tau 21. So this is the final form. 1 by tau 2 is 1 by tau 20 plus tau 21. And if you solve it, you will get tau 2 is equal to tau 20, tau 21 divided by tau 21 plus tau 20. Now tau 20 you can easily find out what is this is radiative lifetime, right? So it is related to the Einstein coefficient. It is inversely related to the Einstein coefficient. So one tau 20 is nothing but 1 by A20. Tau 21 is nothing but 1 by A21. So A20, A21 is already given. So, A20, what is A20? A20 is given 1.2 into 10 to the power 8 second inverse. 1.2 into 10 to the power 8 second inverse. And A21 is given 8 into 10 to the power 7 second inverse. Right? So you can easily write out what is. So but try to put everything in the same order. So if you see it is 10 to the power 8 order, so try to write the second in the 10 to the power 8 order only. So if you see it is 8 into 10 to the power 7, that means you can write it as point 0.8 into 10 to the power 8 second inverse. Now if you put A20, A21 in this form, you can easily find out what is tau 20, which is 0.83 into 10 to the power minus 8 second inverse. And what is tau 21? It is equal to 1.25 into 10 to the power minus 8 second inverse. Okay. So if you put it, now you already got what is the value of tau 20 and tau 21. If you put it, then you can easily find out what is the mean radiative lifetime of this transition, of this excited state E2. So the final form, final value you will get is around 0.5 into 10 to the minus 8 second inverse. And there is another way to solve this problem also. So if you have two Einstein coefficient, so here you will see the atoms are populated in this E2 level. Okay, and there are two transition, which is A21 and A20. So if you have, if Einstein coefficients are given, what you can do, you can find out what is the total Einstein coefficient for this energy level. So total will be A20 plus A21, right? And A20, A21 is given. You can directly put what is the value of A20 and A21. From that, you can find out what is the A2, what is the Einstein coefficient, mean Einstein coefficient for this excited state E2. From that A2, if you take the inverse, you can easily find out what is the mean radiative lifetime of this level A2. So this is the shortest way to solve this problem. Otherwise, you can find out what is tau 20, tau 21. From that, you can find out what is tau 2, uh, which is the method, this method, or you can uh, use this method also. Okay, any of this method will give the same value. So, is the fourth problem is clear to you? So it's a tricky one. If you know how to solve it, then you can easily find out what is the mean radiative lifetime. So I have followed two methods. One is So I followed two methods. One is where I find out what is the total Einstein coefficient A2. From that, you can easily find out what is the mean radiative lifetime. Otherwise, you can also follow this formula to find out the solution. So, is the fourth problem is clear to you, or do I need to go through it again? So, let us move to the next problem then. So the next problem is consider a three-level laser system with lasing between the levels E2 and E1. The level E2 has lifetime of 1 microsecond. Assuming the transition, so let me show the schematic. So there are three levels E3, E2 and E1. Okay, and the lifetime of E2 level is given, which is 1 microsecond. Assuming the transition from E3 to E2, that is this transition, to be very rapid. It is very rapid, so it is rapid. Then estimate the number of atoms that needs to be pumped per unit volume from the level E1 to reach threshold for achieving population inversion. And what is the number of atoms at E2 for threshold condition? So it is similar to the problem we've go through in the three level system, I think. So and the total population density is also given. So it is asking about what is the population in the threshold condition and what is the pump rate at the threshold condition. So it is saying so this is the three level E3, E2, and E1, and the transition from E3 to E2 is rapid. So by rapid, we means whatever atom that is pumped from this first level to this level, this atom will rapidly decay to the second energy level. So in this condition, we can take the population of this E3 level as zero because it's a rapid transition. So whatever atoms are going to are coming to this third energy level, it is decaying to the second energy level. So that means N3 is 0. So N3 is 0 means the total number of atoms, you can write it as N1 plus N2. And at threshold, what we have? Delta N is 0. Now, what is delta N for this three level system? So please, whenever it is delta N, please see what is the level at which the lasing condition is happening. So lasing condition is happening between this second energy level and the first energy level. So that means delta N is nothing but N2 minus N1. And at threshold, it is delta N equal to 0. So that means N1 is equal to N2. Okay. And if N1 equal to N2, if you put it in this equation, you can easily find out what is the population of this second energy level at threshold condition. N is already given 10 to 119. So N2 is 10 to 119 by 2 per centimeter cube. Now, if you want to find out what is the pump rate, so pump rate is nothing but is N by 2 into WP, right? And at threshold, it is nothing but N by 2 into T21. This we have already seen. So T21 is already given. The lifetime is given as, if you see, the lifetime tau 1 is given 1 microsecond. 1 microsecond. So that means T21 is 1 by 1 microsecond, which is 10 to the 6, right? Per centimeter cube. That means the rate of pumping is 10 to the 6 per second. Okay, so to find out the rate, we have to multiply it with the number density also. The rate of pumping would be T21 and divided by 2. So 10 by 6 per centimeter cube. And this is n divided by 2. N divided by 2 is already given 10 to the 19 by 2 centimeter cube. From that, you can easily find out what is the pumping rate. So this will be the last problem that we'll solve. Then we'll move to the next next concept. So the last problem says, in a three-level system, what is the relation between the spontaneous emission lifetime from level 2 to level 1 when it is pumped using three different pump rates, such that WP3 is greater than WP2 greater than WP1. So it's given it's a three-level system. So there are three levels and it is pumped using three different types of pump. So WP3, WP2, and WP1. And WP3 is greater than WP2 is greater than WP1. And it is asking about what is the spontaneous emission lifetime from level 2 to 1 when it is. So what is the relation between the spontaneous emission lifetime between 2 to 1 in these three different pumps? So if you see the gain curve, so gain curve is like this. Okay, so I think for three level we have WP should be greater than T21, right? For three level, and if WP3 is greater than WP2 is greater than WP1, so that means T21 is greater than T21 is greater than T21 1. So that means this is only related to the threshold condition. If you know the threshold condition, you can easily find out what is the answer to this question. So the answer will be option D. So are these six problems clear to you? So I've solved six problems that is related to three level system. So if you have any doubts in any of this problem, then please ask me anytime. Otherwise, we will move to the next concept that is taught on this week. It seems these problems are clear to you. So, okay, so let's move to the next part. So, in the next part, we study about what are the different type of amplifier that is used in the practical application. So, optical amplifier, it is based on the laser action. So, as we know, in laser we amplify the input signal. So, optical amplifier do the same process also. It is also based on the laser action. So that means it amplifies the radiation by stimulated emission. Okay, and if you can divide, there are mostly two different types of amplifier. One is rare earth doped laser amplifier, and other one is semiconductor optical amplifier. Okay, so semiconductor optical amplifier, we won't learn this course. Will only see what is the rare earth doped laser amplifier for this course. And one of the example, so the examples of this rare earth doped laser amplifier, one is neodymium yak, neodymium glass, erbium silica, and ytterbium silica. So these are four examples of this rare earth doped optical amplifier. So first two, it is based on four-level laser amplifier, and the second, the erbium silica, and the ytterbium silica. It is quasi three-level amplifier. We'll see what is quasi three-level amplifier, and this doped element, that is neodymium, erbium, ytterbium. It is rare earth element. These are all the rare earth element, and it is lanthanide series. So these are elements of the lanthanide series. If you see the periodic table, you can easily see these three elements are the elements of lanthanide series, and these are rare earth elements. And what the applications are, this Nd:YAG laser. These are used in industrial and medical application, and the ND glass, it is used in fusion experiment, the high energy pulse application, and erbium silica. This we widely use it the optical fiber communication. We'll see today also how it is used to optical and why it is used in optical fiber communication. And the last one is ytterbium silica. It is also used in both fiber amplifier as well as it is used in industrial and military application. So first let us see what is Nd:YAG laser amplifier. So these are the Nd:YAG means we dope neodymium atom in this matrix of YAG. YAG means yttrium aluminum garnet. So we doped neodymium in the YAG matrix. So what happens when we dope in this neodymium in this YAG matrix? So what happens? This neodymium, it will replace some of the yttrium element of this YAG matrix. So when you replace, it will become Nd3. Okay. So if you want to see what is the energy levels of this Nd plus 3 uh, ion, so this is the schematic of this energy level of the Nd plus 3 ion. So one thing you can notice, some of this energy level, some of the energy levels are represented by wide lines, and some are represented by a narrow line. So this wide line and the narrow line, it is related to the lifetime of this level. So if you recall, uh, we have delta E. So lifetime of a level, delta Q, it is 1 by 2 pi tau L, right? This is the lifetime, this we have seen in the lifetime broadening. You recall it is lifetime broadening, right? Line width of the lifetime broadening. So if you find out what is delta E, so delta E is nothing but H delta nu. So that means H 1 by 2 pi tau. So here you can see this delta E, it is inversely related to tau L. So that means delta E is inversely proportional to tau L. So if the lifetime is short, then we will have a spreading in the energy level. And if the lifetime is large, then we'll see the delta E, the spreading in energy level will be narrow. So this is what represented in this schematic. So here this label is broad, it means the lifetime is narrow, it's short, and it is, if you see this level, it is narrow, means the lifetime is large, right? And the other thing that you can notice that now we are indexing this energy level by this notation 4f 9 by 2, 4f 7 by 2, 4f 5 by 2. So these are the notation that is used to represent the energy level. Okay, we'll see how this notation comes. Now let us see the nomenclature of this energy level. So Nd:YAG, so Nd is neodymium atom and it is atomic number of 60. And YAG is yttrium aluminum garnet. It's the host material where we dope Nd:YAG atom. Okay. And the formula, the chemical formula is Y3L5O12. It's a transparent crystal and it is a, these are some of the information that is related to YAG matrix. So refractive index is 1.82 at wavelength around 1064 nanometer. Now we already see when we dope, when you dope neodymium in YAG matrix, some of this yttrium get replaced and the Nd becomes Nd plus 3. Okay, so that means now the atomic number which was previously 60, now it will have 57. And if you see the electronic configuration, so you must be familiar with this electronic configuration. 1s2, 2s2, 2p6, 3s2, 3p6, 3d10. Okay, so these are the electronic configuration of a atom. Okay, this is related to atomic electronic configuration. So if you see the last energy level, which is 4f3. If you see the last configuration, it is 4f3. So that means these electrons, they are filled like this with the 4f cell. Okay, so if you recall the energy, atomic energy level, or these are represented by different types of quantum number. One is, if you recall, so okay, so let me add a slide here. So there are three different types of quantum number that we use to represent a energy level. One is principal quantum number, one is orbital angular momentum quantum number, one is spin quantum number. Okay, so these are different types of quantum number that is used to represent the energy level. And if you take different types of orbital, in each level we have different types of orbital S, P, D, F, and for each we have L is, for S L is 0, for P L is 1, for D L is 2, and for F is L is 3. And if you want to find out for a given orbital, there are different subcells. So for S, we have only one box here. But for P, we'll see it has three subcells. Okay, so it is related to this L. So if L is 1, then the subcell will range from -1, 0 to 1. So minus L2 plus L in steps of 1. And for D, we'll see it is 5. Okay, -2 to +2 in steps of 1. -1, 0, 1, 2. Okay. Similarly, for F, if you find out what will be the total number of subcell we have, it is -3 to +3 in steps of 1. That means -3, -2, -1, 0, 1, 2, 3. So we have 7. So this is what shown here. We have 7 cells, right? 7 subcells. So now we have 7 subcell and it is, let me read it. We have 7 subcell and we have 3 electrons here. So that means electrons will be filled in this manner. The first electron will filled in this manner. And if you want to find out the spin quantum number, so electron, the spin S is half. So that means each one have S equal to half. So total spin is half plus half plus half. It is 3/2. Okay. Now we'll see this electronic configuration. Now we'll see how we can represent an energy level. Okay. So energy level, they are denoted by this notation. 2s plus 1 Lz. Okay. 2s plus 1 is the multiplicity. L is the orbital angular momentum and Z is the total angular momentum. And similarly, if you see the electronic configuration, we have S. Okay. So in electronic configuration, so I am explaining it in detail so that you don't get confused between electronic configuration and energy level. So electronic configuration, it is, if you see, we denote, we have both, we have S, P, D, F orbital, and for each we have L equal to 0 here, L equal to 1, L equal to 2, L equal to 3. And similarly, when we come to energy level, when you want to represent the energy level, we have also S, capital P, capital D, capital F, and so on. And similar to the electronic configuration, here we, for S, capital S, L is 0, capital P, L is 1, capital D, L is 2, capital F, L is 3. Okay. And J, it is nothing but, J is the total angular momentum, which is L plus S. Okay, it is the vector sum of two angular momentum, orbital angular momentum and spin angular momentum. And if you want to find out it is a vector notation, right? So that means it will have value from L plus S to L minus S in steps of 1. Okay, in steps of 1, it will have value from L minus S to L plus S. Now let us see how this yttrium aluminum garnet is represented by using this notation. So for Nd plus 3, you see the last cell is 4F3, right? So it is 7 subcells, 1, 2, 3, 4, 5, 6, 7. And it is 3 electron that is filled within this level. Now if you find out if you want to find out what is S, what is L and what is J for this case. So S is nothing but the summation of the spin quantum number, which is half plus half plus half. So this is 3/2, right? In the spin, so that means you can easily find out what is 2s plus 1, which is nothing but 2 into 3/2 plus 1. So it is 4. Okay. And for L is also summation of this ML. So ML is nothing but these are so for given L we have subcell ranging from minus L to plus L. So for F, L is 3, right? So it is minus 3, minus 2, minus 1, 0, 1, 2, 3. So that means it is summation of ML. So summation of, so for first one, it is minus 3 plus minus 2 plus minus 1. So we take the mod, it is 3, 2, 1. So it is 6, right? So that means we got L is 6. So what is orbital for L equal to 6? It is I. You see this case, it is I. So that means this is I. And for J is nothing but L plus S. So it ranges from the values L plus S, L plus S minus 1 to L minus S. And L is 6. So this is 6 plus, and S is 4, right? So that means this has value from 10 to 6. L plus S is 10 and L minus S is 2. So in between we'll have values in 1. So that means 10, 9, 8. These are correct, right? No. So, sorry, there is a mistake here. So S is, so I took 2S plus 1. So L is 6, S is 3/2, right? Here. So that means J is 6 plus 3/2. So it will have values from 6 plus 3/2 to 6 minus 3/2 in steps of 1. So 6 plus 3/2 is 15/2 and 6 minus 3/2 is 9/2. And it will it will have values in 1. So J, if you want to find out, is 15/2 to 9/2 in steps of 1. Okay. So this is how you can find out what is the notation for a energy level. So these are all I have explained. For J equal to 6, we have values ranging from 9/2 to 15/2 in steps of 1, and in between we have 11/2 and 13/2. Okay. Please go through this notation. If this is confusing, then please try to solve few. Just take any electronic configuration and try to find out what is the energy notation for that state. Now let us see how that, and one condition is the selection rule. So selection rule basically tells about what is the allowed transition in a state. So it's not like if you have energy level, any types of energy transition is allowed. Like let's say you have three, not like every transition, like from 3 to 2, sorry, 3 to 1 and 3 to 2, 2 to 1. So the transition, it depends on the selection rule. If the selection rule is allowed, the probability of that transition is high. And if the selection rule is not allowed, then that probability of transition is it is low. And the selection rule, it is basically a quantum mechanics concept. It's like for each, so if you take the energy level, so if you see this energy level 4f 9/2, 4f 7/2, 4f 5/2. So this energy level, these are represented by wave function. So wave function basically tells about the probability of finding the atom in that energy level. So these levels are represented by wave function, and whenever so different energy level will have different type of wave function. So whenever the atom is making transition from let's say higher to lower state, so the transition will be high whenever the overlapping of this wave function is high. So if the wave function is overlapping nicely, then the probability of transition is high. But when sometimes it happens, whenever it is making a transition, they destructively interfere. So it is the wave pattern, right? So they will interfere constructively, destructively. So whenever there is a destructive interference, then the probability of transition, it is decreases. So this is basically a physical significance of selection. And if you and from quantum mechanics, we find out what is the selection rule is delta S should be 0 or delta L should be 0 or plus or minus 1. So if this condition is satisfied, then we can say the probability of transition is high. And if it is not satisfied, then it is a forbidden transition. That is, the probability of this transition is less. Okay. So please remember this selection rule. Okay. Now, if you see, so let us see how this transition is allowed and forbidden in by taking the example of ND plus 3. So if you see from, so let me take, okay, so let me draw the pattern here. So this is 4F 9 by 2 and another energy level is 4F 5 by 2. So if we take this energy level, so what is the, so this is represented in terms of 2s plus 1 Lz, right? And this is also 2s plus 1 Lz. So for transition to happen between this state, you should follow delta S should be 0 or delta and del. It's not like one condition is satisfied, then it is allowed. We have to see whether these two conditions are satisfied or not. So either delta L is 0 plus or minus 1, or you can check whether delta Z is 0 and plus or minus 1. So you have to see these two conditions, whether it is satisfied or not. Okay, so let's see the first condition. So for first condition, delta S should be 0. So that means if you see this level, S is, what is S? So 2S plus 1 is 4 for this level. That means S is 3 by 2 or 4F 9 by 2. And for the second, for the 4F 5 by 2, 2S plus 1 is again 4, right? So that means S is 3 by 2 again. So that means this delta is equal to 0. It is satisfied. Now let us see whether the second condition is satisfied or not. So you have to check both conditions. So delta L should be 0 or plus or minus 1. So if you see 4F 9 by 2 is F state, right? For F, what is the value of L? L is, if you see, F is 3. And for 4F, this state 4F 5 by 2, it is also F state, which is L equal to 3. So that means the delta L here is also 0. So this means these two conditions are satisfied for this transition. So this is a allowed transition. Now let us take another type of transition, which is from, let us see this transition 4F 3 by 2 to 4I 9 by 2. Okay. So we have see 4F 3 by 2 to 4F 9 by, sorry, 4I. Let me write it again. 4I 9 by 2. So let us check the first condition. Delta is 0. So delta S is already 0 because 2S plus 1 is 4 here and 2S plus 1 is 4 here. That means S is equal. So this is satisfied. Now the second condition is delta L should be 0 and plus or minus 1. So it's for 4F 3 by 2, it is F state. That means L is 3. And for 4I 9 by 2, it is I state. That means L is, you see, for I, it is 6. Right? If you see this one, it is 6. So that means the delta L in this case is 3. Right? So that means this is not the second condition is not satisfied. So this is the selection rule is not followed. So that means the probability of making a transition from this state to this state is low. And the situation where we encounter this kind of condition, we state this state is a metastable state. So the definition of metastable state is So metastable state, by metastable state we mean state which a longer lifetime. So why longer lifetime means the atoms that is longer time. So why it is it's because of the forbidden transition. So because of the forbidden transition, the probability. So in this case, the selection rules are not followed. So because of the selection rule is not followed, we see the probability of transition from the metastable state to a ground state is very low, and that is why we say this is a metastable state. So you can easily find out what are the metastable state if you find out whether this state is following the selection rule or not. If it is following, then this is not a metastable state. If the state is not is following a selection rule, then this is not a metastable state. And if it is not satisfying the selection rule, then it is a metastable state. So metastable state do not follow the selection rule. Okay. Now, if you want to see, so let us see what is the laser transition in a Nd:Arc laser. So in a neodymium atom, depending on the, so you see there are different energy levels. So there are three higher energy state. There is a metal stable state here. There is a ground state. So depending on the source which we use for the pumping, the atoms will get excited to any of this higher excited state. So either it will get excited to 4f9 by 2, or it will get excited to 4f7 by 2, or 4f5 by 2. So the two types of source you can use is krypton plasma or laser down. Okay. So depending on the laser, so what so whether we use krypton or whether you use laser, what will happen? The transition in the higher state, that is, let me remove this. So the transition in this 4f state. So the transition in this state is very fast. So that is why we can represent this level as a single level. So all these 4f 9 by 2, 4f 7 by 2, 4f 5 by 2. So the second level is the 4f 3 by 2, which is a metal stable state. And there is also intermediate state where the transition is also fast, where the lasing happens. So if you see, there are mm, there are three different radiation that can happen that can emit during the lasing condition. One is 980 nanometer, one is 1064 nanometer, and one is 1319 nanometer. So 980 is from 4f3 by 2 to 4f3 by, so let me take other color. Okay, so 980 is from 4f 3 by 2 to 4i 9 by 2, and 1064 is from 4f3 by 2 to 4i 11 by 2, and 1319 is from 4f3 by 2 to 4i 13 by 2. So these are the these are the wavelengths we'll get during the lasing condition. But if you see the probability, so probability of this getting this 980, 1064, and 1319, you see the probability of getting 1064 is high. 10, it is around 55%, and probability for 980 is 30%, and 1319 is 14%. So that means the prominent line in this Nd:Arc laser is 1064 nanometer. So if you now instead of uh, instead of showing this energy level in detail here, we can show the schematic like this. So all these level where the transition is happening first, we can represent it as a 4f state, and there is a metal stable state here, and there are three state where also the transition is happening very fast. So we can represent it is by 4i 11 by 2 and The last one is the ground state. So this is how we can simplify the energy level diagram. Okay. In the schematic of NDR laser is the same one. We use krypton flash lamp or any laser diode. We use this to pump this NDR medium, amplifier medium. And when we feed a weak signal of 1064, it get amplified in the output. Okay. In the if you want to see what are the typical parameters for the NDR laser, so lambda 0, the prominent line is around 1064 nanometer, and tau L is 230 microsecond, and these are the some of the information about the transition. That is, tau L sigma is the emission cross section, and delta nu is the line width, and n is the total number of atoms, and gamma 0 is the small signal gain coefficient. Okay, so these are the some of the practical values that you can easily get, that you have for a NDR laser amplifier. Okay, so this is all about the NDR laser, which is a 4-level energy system. Now we'll see. So, do you have any doubt in the NDR laser amplifier? Otherwise, we'll move to the erbium doped one. So we'll try to finish the erbium doped in this section, and in the next section we'll try to solve problems as well as the make concept. Okay, so let us see what is erbium doped fiber amplifier. So this is so if you see erbium doped fiber amplifier, it is also the short form is EDFA. Okay, I think most of you heard about this EDFA. So it is widely used in optical communication system. We'll see why it is widely used. So for optical communication, what we need? Optical communication, we need optical fiber. Okay. So all kind of mobile communication or any information, the information we need optical fiber. So optical fiber, if you see, so let me give you a short intro to the what is optical fiber. So optical fiber, it is nothing but the medium where we can transmit information most efficiently. So if you see what are the components of optical fiber, it is made up of two. What is one is core and another one is cladding. So it is core and cladding. So the inner, if you see the schematic, it is a circular cross section optical fiber. So the inner one is core. This is core, and this one is cladding. And in this medium, we transmit light by total internal reflection. So TIR, I think all of you know. So if we have two different medium, N1 and N2, and the refractive index of N1 is greater than N2, whenever this condition is satisfied, and when the light, when it falls at critical angle at this interface, what will happen? It will reflect it back to the medium. Okay, so in this way we can see that light is propagating along this core because of total internal reflection. Okay, so for total internal reflection, we need one of the condition is N1 should be greater than N2. So that means the refractive index of the core is greater than N2. So how we can increase the refractive index of N2? So we can increase it by doping it. So before going into the details of N1 and N2, let's see what is the gain in the optical fiber. So gain, it is represented by I by I0, which is e to r gamma L. And this optical fiber, they provide long interaction length for amplification, and we can guide the information without any diffraction in optical fiber. Okay, so and if you want to now let us see how we can increase the N1 in the core layer. So to increase it in the telecommunication fiber, what we use, we dope the silicon by germanium. So GeO2, we dope the inner core by GeO2. So in this case, the refractive index become 1.46, and for silica, which is the cladding layer, it is 1.45. So as I said, the germanium is GeO2 is used to increase the refractive index of the PDA. Now, there are some drawbacks of using germanium oxide. So what we can do, and there are some advantages of using erbium in the core layer. So we'll see what is the advantages. So now if we, instead of GeO2, if we dope erbium oxide in the GeO2 and SiO2 matrix, what will we see? We'll see a flat gain curve. Okay, we'll see a flat gain curve during the transmission. And these are some information about the fiber, that is numerical aperture. So numerical aperture, it is nothing but what is the angle up to which you can uh, incident the light in the optical fiber. So if you have optical fiber and if you launch light at this angle, so there exists a maximum angle up to which this light will be guided. So that is the numerical aperture. Okay. So it is related what is the maximum angle up to which it can guide the light. And what happens? So now we are doping erbium in the silicon matrix, right? And silica, it is a glass, right? Okay, Vishal, do you have any doubt? I saw you writing something in the chat box. So do you have any doubt? Not able to solve week 4 assignment question 9. Could you please give me a hint on how to solve it? Week 4 assignment question 9. So let me see the question first. Week 4 question 9. Please wait for some time so that I can log into the NPTEL site. So okay, it is also based on EDFA. So it is telling in a particular EDFA with 10 meter long EDF, assume that the signal amplification follows an exponential relation up to a certain length Z0. The pump power given to the system at Z equal to 0 is 500 microwatt, and it reduces to 100 microwatt at the output end of the fiber. The input signal at Z equal to 0 is 10 microwatt, given that at Z equal to 0, the pump power is 150 microwatt, the signal power is 200 microwatt. The small signal gain coefficient of the EDFA is okay. So let me see what is given to this problem. So it is a 10-minute long PDF. Assume that the signal amplification follows an exponential relation of 2s at tangent z0. And the pump power given to the system at z0, that is WP z0, is 500 microwatt and it reduces to 100 microwatt. Okay, at the output end. The input signal power at Z0 is 100 microwatt. Sorry, 110 microwatt. Given Z0 in microwatt, Z equal to 0. Signal power is 200 microwatt and the pump power at this end is 150 microwatt. The small signal gain coefficient of ADF. So small signal gain coefficient, I think they are asking about what is the value of gamma 0 nu. Okay. So it is asking about gamma 0 nu. So first you have to find out what is gamma nu, right? So you know already gamma nu is already related to gamma 0 nu 1 plus I nu by I. And all this information are already given. This information, if you see the signal power is already given, signal intensity is already given. From that you can, and the length is also given, and it is telling it is following a exponential relation. So from this relation you can easily find out what is gamma, right? From gamma, if you want to find out gamma, then you can, using this relation you can easily find out what is gamma 0 nu, right? So use the relation. It's not like every information is important in this question. Whatever the parameter you need, just look for that parameter, and it's already given. All the parameter is already given. Use this parameter to find out what is the gamma nu. Okay, first find out gamma nu, then you can easily find out what is the small signal gain coefficient. Okay. So it is telling the intensity is decreasing, right? And it is following a exponential relation. So you know I equal to I naught e to power gamma L. So from that you find out what is the appropriate values and find out what is the small signal gain coefficient. Okay, this is all about what is the small signal gain coefficient for EDFM. Okay, so let us quickly go through the EDFM now. So what I was telling. So glass, glass is not a crystalline material. So it's a amorphous material. So that means the periodic arrangement of the silicon and oxygen in this glass matrix, it is not periodic. Okay, so it is amorphous. Glass is amorphous material. So that is why there is a there is no periodic arrangement of silicon. So some of the atoms it may be arranged like this. Some atoms are arranged like this. So you will see a different type of arrangement in this glass matrix. Now in this aperiodic crystal, when you dope erbium, so when you dope erbium, what will happen? So uh, if you see erbium here, so here the arrangement is different. Here the atomic arrangement is different. So depending on this arrangement, what will happen? The energy will split. Okay. So we'll see a splitting of energy level due to this aperiodic arrangement of atoms in the lattice. So that we say Stark split energy level. Okay. So if you recall, one type of, I think, inhomogeneous broadening, there is the example that is whenever there is a inhomogeneity in the lattice, inhomogeneity in the arrangement, we'll see the energy level will split and we'll see multiplet levels in that case. So this is what represent here. So if you see this one, there is a multiplet of 4i 9 by 2 of with 5 nanometer, and for 4i 11 by 2 there is a 5 nanometer splitting. So this splitting happens uh, because of aperiodic arrangement of Si and O2 in the glass matrix. And what will happen? So because of this multiplets level, we'll see different types of transition. So if you see these two levels, so it may happen the transition will happen from here to here, here to here, or here to here. So depending on this, we will see there is different emitted wavelengths in the lasing condition. Okay. Now, if you see the transition, so for this, for the top level, 4i 9 by 2. So there are multiplets of level 4i 9 by 2. For 4i 11 by 2, it's also multiplets of level. And 4i 13 by 2, it's also multiplets of level. So because of this, we will have different types of pump. So we can have 800 nanometer pump or 980 nanometer pump, or one is 1480 nanometer pump. So all types of pump can be used to excite the system and to achieve the population inversion in the system. And the population inversion, it is basically happening between these two states, this state and this state. So that means, let me clear all this. So So that means this the transition happening here and 4i 9 by 2 and 4i 11 by 2, it is a first transition. So because of this first transition, the atoms get accumulated in the 4i 13 by 2. So that is why it is a tau a lifetime of 12 milliseconds. So if you see the tau here, it is the for upper state it is in the order of microsecond, but if you see 4i 13 by 2, it is millisecond. So that means it is the metastable state. Okay, so we'll see a lasing condition between these two levels. So now it is almost time. So let us discuss all the details in the next section. All the concept as well as all the parameter we'll discuss in the next section. So till now, do you have any doubt or any particular doubt about the assignment? You already asked about one question. Do you have any doubt in these slides? Okay. Okay, so let us discuss the details of this ADFA in the next section. Thank you for joining this section. I think whatever I have solved, whatever problems I have solved, it is clear to you, and the concept is also clear to you. If not, we'll meet on next Saturday, same time, 4 to 6, where you can clarify your doubts as well as the conceptual doubt, assignment problems, uh, anything, anything you can ask me in the live section. And one thing I request, please try to attend the live section because not everyone is not attending the live section. Only few people are attending the live section. So please try to attend it because it is also beneficial for you to clarify your doubts immediately as well as to go through the concept. So now let me end this section. We'll meet on the next Saturday. So thank you for joining the section. Bye for now.